let's pick up where we left off. Okay, so I just introduced a couple of different groupings, I guess you could say, of oxidizing agents that we commonly use, right? We said we had items that had OO single bonds, and then items that had metal oxygen bonds. All right, let me highlight just a few of the more specific type of compounds and families that we see in there. All right. First, let's talk about the ones that have OO single bonds. All right. First of all, probably the most obvious one in here, obvious ones, are going to be the ones that are just composed of oxygen, right? You have molecular oxygen, O2. You also have O3. Anybody know what O3 is? Ozone, yeah, ozone. Both very, very good oxidizing agents. Heck, you guys have seen firsthand the oxidation effects of oxygen. Have you ever seen rust, right? Air oxidation of iron by oxygen into iron oxide. Right, so yeah, those are two excellent oxidizing agents. You also see what we call peroxides, and we're going to see a couple of peroxide derivatives here in a second as well. All right, peroxides, they have the general form ROOR. And in most cases, you know, this is going to mean, the R group is going to mean that you have a carbon chain. Although there is one specific one, and the most common one that you guys have probably heard of, that has H's instead, and that's hydrogen peroxide. There's another one you might have heard of. I'm not going to draw the structure because it's really big. The benzoyl peroxide. And a bunch of others as well. So, you know, those are just a couple of examples to give you the idea. But they all have this OO single bond in them. Very, very easy to split. You guys ever heard of benzoyl peroxide? Do you know where you've heard of it? No? Very common in skincare products like acne medications. Clearasil, that type of thing. Very, very dilute amounts. Concentrated benzoyl peroxide is explosive. And it's shock sensitive too. You smush it, boom. So yeah, think about that happening to your face next time. All right. It would be neat. All right, so those are peroxides. And we have a couple of related families of compounds that are also useful. We also have the peroxy acids. And those are sometimes known as peracids. It's just the shortening of the name. They have the structure very, very similar to a carboxylic acid. However, instead of just an OH attached to a carbonyl carbon, it's got an extra oxygen. So that's where you cleave the bond in order to get a redox reaction. All right, there's one very particular one that we're going to use a lot. I want to go ahead and just highlight. And that's that. That one is called metachloroperoxybenzoic acid. However, you'll probably see it referred to as MCPBA for short. You know, we chemists love our acronyms. That's particularly going to be used a lot for one type of reaction that we're going to see here in just a few minutes. It's not the only one you can use, but it just so happens to be so commonly used. it's worth highlighting. All right. But of course, there are a lot of other good peroxy acids out there. Right. Okay, so one other one I want to mention is the peroxy ester. And if you're looking at context here, you saw with peroxy acids, it was, really similar to a carboxylic acid, basically just with an extra O. That's kind of what peroxy esters are, right? It's the same thing as a peroxy acid, except instead of an H right here, you have another R group. All right. So yeah, those are by no means all of the oxidizing agents that fall under this category, but those are probably some of the most commonly used ones. And those are going to be the ones that we really focus on in this particular chapter. Okay? So far, so good? All right. All right, let me give you a few examples of ones that fall under this category. Metals, metal oxygen. Again, there's several examples, right? There's no way we're going to go over all of them. But some of the more common ones you've probably heard of, and in fact, probably worked with before, right? Anybody ever worked with potassium permanganate before? Y'all remember that? It's purple. You ever work with purple stuff in the lab, get it on your hands, it stains you for a few days? If not, wow, then you haven't really lived as a chemist. It goes away after a few days. But yeah, potassium permanganate. It's got a central manganese ion, and that manganese ion has multiple oxygens attached to it. I'm not going to draw the structure of all these, but I'm just going to sort of use this one as an example. That's the structure of the permanganate ion. And of course, potassium permanganate's a salt. It'll dissociate. Potassium goes away. We don't care about it. This is the important thing, right? This is the source of your oxygens, which actually act as the oxidizers. Right? And the other metal oxygen oxidizers, they're kind of similar to this, all right? And there's certain ones that are used a lot. Manganese is used quite a bit, especially in this form. Another one that's used quite a bit is chromium. This is sodium dichromate. Y'all ever used sodium dichromate before? Maybe, or potassium dichromate. That's also used quite a bit. Let's see, what else has chromium? CrO3. It's chromium trioxide. There's also another one called pyrididium chlorochromate, but we generally call it PCC for short. So yeah, chromium is used quite a bit in oxidizing applications. And we're going to see later on, the source of chromium can actually determine its oxidizing strength. These aren't all necessarily created equal as far as how strong they are, right? In fact, PCC is notably weaker than the other three, right? We're going to see an example of that. Let's see, there was one more. Oh, fun times here. Have you ever used osmium before? I bet you haven't. Well, guess what? Now you are. We're going to see, you can see that osmium is also commonly used as an oxidizer in the form of osmium tetroxide. Okay. I don't even know where osmium is on the periodic table.
76.
Which one?
76.
You answered that really fast. It's like you were already kind of curious and looking for it, weren't you? It's not a bad thing. It's a good thing. Yeah. So yeah, nobody ever uses osmium for anything in Gen Chem. This is the only time we'll use it in organic. All right. So yeah, that's a little smattering of some of the stuff that you can use as oxidizing agents. So let's see it in action. First of all, any questions before we move on? Okay, let's see it in action. All right. We're going to look at a few different groupings of reactions. First one is called epoxidation. Oh, we're going to start off with a favorite. Yeah, epoxides. We've seen epoxides before. We've done reactions with them. Hey, you get to learn how to make them now. Isn't that fun? Yeah. What you do whenever you do an epoxidation is basically that you take an alkene, and you add a peroxy acid, and it becomes an epoxide. So as an example of this, we could say, let's just look at the simplest example. You could take ethene, sorry about that. You could add peroxy acid. Far and away, the most commonly used peroxy acid for this purpose is MCPDA. You can use others, but that just happens to be a really commonly used one. And basically what happens whenever you add this oxidizing agent is that this carbon-carbon double bond will break, and you're going to form two new carbon-oxygen single bonds. And there you have it. You have an epoxide. All right. Now, what have I not done here? I haven't gone over the mechanism, right? And I'm not going to. If you want to look at the mechanism for this, you're more than welcome to. It is in your book. However, from experience, I have found a lot of these oxidation mechanisms are complex, convoluted, and I've found that even though I hate to use the M word, memorization of this actually tends to work a bit better, just for this little section, just for these oxidation reactions. So it's pretty easy, I think, to remember the fact that whenever you have a 2-carbon unit in an alkene, that 2-carbon unit will be converted to an epoxide every single time. You're more than welcome to look at the mechanism, though. No, we're just not going to go. Okay? All right. Let's look at another one here. All right. This is another alkene. And I don't know if you've noticed or not, but I drew it in a certain stereochemical fashion. What did I draw? What's that? It's not E. It's not Z. You're close. It's cis. Since it's di-substituted, we use cis trans. Right? So yeah, that's a cis version. All right? Now, I didn't mean to draw these so close together. Here's something to keep in mind whenever you're doing an epoxidation regarding stereochemistry. You will frequently start off with an alkene that has a certain stereochemical arrangement. You might have a cis alkene, you might have a trans alkene, you might have an E, you might have a Z. Right? Whenever you do this reaction, stereochemistry is preserved. Right? Think about it. you have cis trans, whatever, in an alkene, right? What's the other situation where you can look at cis trans? What other context? Not just with alkenes, but also with, you guys know this. What other type of molecular structures did we see cis trans with? Oh, you guys are gonna hate yourselves. Or me, possibly. Rings. Remember, you have a cyclohexane ring or something like that? You have two things hanging off of it. You know, like, you know, two methyl groups or something. If it's like that, it's what? Cis or trans? Trans, right? If they're on the same side of cis. Well, guess what? You're making a ring structure as a product. So when you draw an epoxide, you got to ask yourself, okay, well, I'm making a ring. How are these two substituents, this ethyl group and this methyl group, going to be related to each other stereochemically, right? Well, there's a simple rule for that. Stereochemistry is preserved. That means if you start off with a cis alkene, guess what type of arrangement you're going to get on the ring? That's your cue. Cis, thank you. So these two guys are going to be on the same side. They're on stereogenic centers, so you got to use the dash wedge notation. I did not draw that very well. There we go. Yeah, so you see there, they're represented as being on the same side. However, don't forget, you can also get a mixture here. Because you could have that as well. I think you would find those are two different molecules. These two are not identical, right? So basically, this is strictly speaking, it's not syn addition, but kinda it is. So we'll say it's close enough. It's not really syn addition since you're not adding two things to it, but you are adding something to each one of the carbons. So, you know, kind of like that. But because of this sort of pseudo syn addition, these guys are always going to be on the same side. Yeah. Any questions on how we got that? So far, so good. All right. All right. How about this one? I'm gonna get used to looking at something kind of weird looking. Well, we got a peroxy acid. We got an alkene. We know we're getting an epoxide, right? That should be automatic. All right, so you know you get that. All right. But again, go over your mental checklist. Look at your product. Did you make any new stereogenic centers? See some nodding. How many did you make? 1, 2, 3, 4, 5. How many new ones did you make? You guys are extra shy. By the way, I don't mind if you say it wrong, your answer. So don't be afraid of saying it wrong. You learn a lot. I mean, I'm gonna stare at you awkwardly until somebody says something. Thank you. Yes. Yeah, we made 2. 2 new ones right over there. Okay. Bless you. All right. So we know stereochemistry should be preserved. And that's actually pretty easy to see here because it's a ring. You know, everything's kind of locked into place, so you don't have a lot of options. We still need to draw each stereoisomer that we formed. Okay? There's a couple of different directions that oxygen or that peroxy acid could have approached from, right? Remember, these guys, they're sp2. That means they're trigonal planar, flat as a sheet of paper. So that epoxidation could have occurred from the front side and if it occurs from the front side, you get that. And that looks really weird. You guys haven't seen like the dash wedged epoxide bonds before, but if they're attached to another ring, you have to use it. So yeah, if it came from the front side, you would have gotten that. If it came from the back side, you would have gotten that. And you do, you get both of them. So that's important to realize. Don't forget, when looking at stereochemistry, number one, stereochemistry is preserved, but also, you know, the fact that these carbons, since they're planar, they can be attached from either side. Okay, does that make sense? Are there any questions about that? We're actually going to use this reaction, epoxidation, as a basis for the next reaction. Okay. All right. The next type of reaction we're going to look at is called dihydroxylation. Hey, what type of groups do you think we're using here? Give you a gold star if you get it. What? What's that?
Single bonded oxygen.
Single bonded oxygens. What kind of single bonded oxygen? What type of group? What's the functional group called? What's the functional group called in dihydroxylation? What's that? Hydroxy groups. Yeah. How many of them are we adding? 2, because it's di. Yeah, this is a way for us to get 2 hydroxy groups on the carbons in a double bond. Right? So basically, you got an alkene. This is a way for us to get OH groups on consecutive carbons. This is called a couple of different things. It's called, first of all, it's called a diol because there's 2 of them. Since they're on, actually this would not be vicinal, just general. This would be vicinal. That would be called a vicinal diol because they're on consecutive carbons. Also known as a 1,2 diol. Those are synonyms. How do you do this? Well, it's a two-step process, actually. All right. The first step is to add a peroxy acid. That should look familiar. Why? We just did it. So the first step in this process, first step of this particular type of dihydroxylation is to do an epoxidation. Right? So you make the epoxide first, and then you add water in the presence of either acidic media or basic. So in the presence of H plus or of OH minus. Different ways to do it, but it gives you the same results. All right. So let's take this a little further. Let's see how this occurs. All right. If we had a peroxy acid to this, right, we know we get an epoxide. So we can draw our epoxide. We didn't make any stereogenic centers, so we don't have to worry about stereoisomers. And then you have your H2O out here. And just for fun, let's say we have it in the presence of H plus. Again, this can work a couple of different ways, a couple of different mechanisms, depending on if you have H plus or OH minus. We're going to use this, all right? Well, we'll look at a little snapshot of the mechanism. If you have this arrangement, what do you think is going to happen? An epoxide with water and acid. It will be broken open, not immediately though. Something's going to happen first in this case before you get a breakage. You got that H plus out there, what do you think it's going to do? Yeah, this will protonate first. We have a protonated epoxide. And then that water will come in and break the ring. Okay. Now, if you were doing it with OH minus, the mechanism would be a little different. In that case, the OH minus would break open the ring, and then the water would protonate that oxygen. Okay. There'll be one deprotonation step, and eventually you end up with, I guess, just for visual purposes, I'll draw like this. You'll end up with your diol. Right? Note this. Where do your oxygens come in from? Is this a syn addition? Is this an anti-addition overall? What? Both? Anti, yeah. In the epoxidation, your oxygen came in from one side to make an epoxide, and as we've seen before with epoxide reactions, they get attacked from the back side. So specifically, this is called an anti-dihydroxylation. We'll see there is a syn one, but it works a lot different. Okay, so anti-dihydroxylation, number one, make an epoxide. Number two, you break it open with water. All right, does that make sense? So far, so good? All right. All right, let's take a look at another one. Let's take a look at this one again. All right, let's go back to this guy. All right, so first we're going to do an epoxidation, MCPDA, then add some water. Oh, we'll just do it in the presence of base this time. And let's see what happens. All right. Well, what's the overall, just very blandly, generally speaking, what's the overall effect after all this? The carbons in the double bond at the very end are now going to be transformed into what? What's that? Thought I heard something. Well, that will be an epoxide after the first step. By the very end, what are those carbons going to have on them? OHs, right? So you know. It's going to be OHs on both of those, right? Well, let's use our powers of deduction here. All right, we know we get that, first off. Check for stereogenic centers. Did we make any new stereogenic centers? If so, how many? I see like 3 of you doing this. Like, yeah. It's like you're trying to, it's like you're bidding at an auction, but you don't want anybody to see you, so you're like, okay. Yeah, you make two new stereogenic centers, right? So you know you've got to represent the stereochemistry here somehow, right? Well, what do you know about the stereochemistry of hydroxylation here? What do we say it was? Sin or anti? Anti. So that means the OHs have to be in opposite directions, right? So getting into it brick by brick. All right, so you ask yourself, how can these OHs be aligned opposite to each other? You know, there's a couple of different ways. You know, you could have that, or possibly you could have this. That leads you to the final answer. So even though we're not strictly going through the mechanism here, and you can also kind of ask yourself some logical questions in order to get there. Okay. Does that make sense? Any questions so far? All right. We're almost out of time. I do want to introduce the next one though, real quick. That is sin dihydroxylation. Yeah, we can get those OHs on the same side as well. How do we do it? Totally different. We wanted to do a sin dihydroxylation. And I'll just use that again as an example. Use a strong metal oxidizer. Just OH minus, yes. And there's 2 different ways you can do it. You can either use the KMNO4 H2O and OH minus system, or you can do a 2-step process. Number 1, osmium tetroxide. Number 2, sodium bisulfite and water. oops. It's a 3, not a 4. They both give you the exact same thing, right? Not just for this example, but for any syn dihydroxylation. All right, and it's exactly what it sounds like. The two OHs end up coming from the same side, always. So you could approach it just like you did the last one, right? You know, both of the carbons on the alkene get an OH. You know they got to be on the same side, so there's a couple of different ways you could do it. Could be like this. Or it could be like this. They're both correct. They're both syn. Now, why does it do this? I'll have to wait till next time. All right, any questions on this stuff? Hey, we need to talk exam 1. Woo, yeah, everyone. All right, first exam is going to be coming up soon. We're going to schedule the first exam for next week, next Wednesday and Thursday. Not this one, but the following one. It'll cover 3 chapters. It'll cover chapters 10, 11, and 12. All right. I do want to give you a heads up. These are not open book, open note. I was only doing that. I know, Gray. I know. I was only doing that. That was a sort of a compensation for you guys not having in-person class. That was an anomaly. That's not something I do on a normal basis. So just wanted to give you a heads up on that well in advance so you'd be prepared. Okay. Otherwise, it's going to be basically the same. You will take it during your lab period in the lab room. All right. Okay. That's all I got. 10, 11, and 12. Yeah, so the end, basically the end of this chapter. We'll mark the end of it.